So today we're gonna start with the last few slides of the last packet. And we're talking about compositions in the hydrologic cycle. We did some general discussion and we talked a little bit about rain, the processes that are involved. So next, I want to just briefly mention rivers, and then we're going to go back to rain for the rest of the time today to talk about acid rain. So rivers, just like rain, have various ways in which solids can get into them. And because many rivers traverse a large landscape and lots of different bedrock conditions, slope conditions, etc., they really get an integrated composition. So depending on where you sample them, near their headwaters, near their outflow, or anywhere in between, you get really different compositions. And there's a lot more impact of interacting with solids in the environment than we get in rain, especially silicate weather. The other thing that's really different about rivers is that they have a lot of particulate material in them, which for rivers we call suspended load. So we distinguish between the suspended and the dissolved forms of material. So just like every other setting, we have TDS, right? And the total dissolved solids reflect these kinds of processes that we've already been talking about: inorganic reactions, biological phenomena, and various kinds of water sources. So stuff that comes right out of the sky is going to look different than groundwater or lake water. And as we talk about those settings more coming up, maybe you'll appreciate that even more so. But in essence, because of the residence time effect and biological activity, we tend to get really distinct compositions in those. Now, suspended load is kind of independent of that. Suspended load is more to do with a combination of what rocks we have in the environment and what is the relief of the watershed. It's really steep. It's really steep, then we're going to be having a very energetic river, and which means it's got a high gradient, is defined there. And that's going to transport more particles. So generally, when we find high relief basins, these are in geologically young environments. This is why we have high relief here, because on the geological perspective, all these islands are very young. So that's a key feature, but there's some other features too, such as what is the rock in the area, how big is the watershed, what is the temperature, and I'll hopefully illustrate this for you in a moment, how that works. This is a table of the kind of 20 biggest rivers, with the last 3 being tied with each other. There's a bunch of different things on here, such as how much water comes out in cubic kilometers per year, what's the total dissolved solids, what is the total suspended solids, what's the ratio of those two things, what's the drainage area. So you could go through and look for various relationships on your own. There's always exceptions to the rules, but there's some of those things I mentioned on the last slide kind of show up here. And the key thing to note is that if you're only going to look at one river on the planet, you look at the Amazon, because look at how much bigger it is, how much more water that comes out of it, and look at how high the total dissolved solids are. And the interesting thing, which I've highlighted here, are the highest and lowest dissolved to suspended ratio, right? So you can see there's a big difference there, right? 2 orders of magnitude difference. St. Lawrence River, which flows in northeastern North America in a very old terrain, low relief in general, tends to have a different kind of compositional profile from the perspective of what's dissolved and what's transported in solids relative to what we find in the Amazon. And this is just a map view. This comes from Burner, reading that you're supposed to be doing. And it kind of shows you where the most, suspended load, particulate load runoff is. And it's these kind of cross-hatchered areas. And they're all places with high mountains in them, as you can see. And those are all geologically young. Even these black, which is the next highest after these 2 cross-hatched ones, all of the western side of North America, the Amazon basin, is part of tectonically young Southern Europe, et cetera, et cetera. So, and there's some human effects on this sediment load. We both increase and decrease them with our activities. Some of the ways we increase them are things like agriculture, tilling the field, breaking up of the soil units that tend to stabilize soil from erosion, deforestation, especially on hillsides, which increases erosion. We can also decrease transport due to putting dams on, for instance, like the Colorado River, before it was dammed, used to run relatively warm and very, very cloudy. Now that it's full of dams, most of that sediment is trapped and it runs cool and clear, and it has effects on the ecosystem there. And then, of course, urbanization has a big effect on runoff. So just like pretty much everything else that we're talking about, when we look at tables like this, we have to think about, okay, when were these measurements made and how much impact of human activities is there on? So when we get to the total dissolved solids and the chemical load, this is a table. You notice here that each of these ions are the same ions that we talk about in seawater all the time, the major constituents: calcium, carbon as inorganic DIC, bicarbonate, carbonate anion, sodium, chloride, sulfate, magnesium, potassium, dissolved silica. And you'll see that there's a couple of different categories on here. The first one is this atmospheric cyclic salt. That is the marine rain particulate nuclei that we talked about last time that dissolve into rainwater. And it comes to the land surface carrying these salts, mostly with the proportion that we find in seawater, depending on where we are. As we move over the continents, this value goes down overall, and over the oceans it's high. And then we look at the three kinds of rocks: carbonate rocks, primarily calcium carbonate, a little bit magnesium carbonate, silicate rocks, evaporites. Is everyone familiar with that term? These are salt mineral deposits that we find. You can find them in coherent rock units. A lot of oil is trapped under salt domes, for instance, off the margins of the Atlantic Ocean. That's from a proto opening of the Atlantic Ocean when the ocean was small and not circulating very well and prone to drying out. The Mediterranean has dried out over, in the deep past in the Miocene, for instance. So there's that kind of evaporite. There's also, if we just put a lot of water onto soils in Western North America and then it dries out, from agricultural practices, that's another form of evaporite. So this salt content looks similar to this. The ratios are a little bit different depending on the sources, but similar-ish to that. And you can kind of see that the weathering of carbonate rocks and watersheds contributes a lot of the calcium and a lot of the carbonate and a lot of magnesium, and not much of the other things, whereas the weathering of silicates gives us different proportions. So as you can imagine, when you look in a large-scale geological map of a particular region, if it's got a lot of this kind of rock or a lot of that kind of rock, this is like Florida is essentially all of this. The Sierra Nevada is essentially all of that. Then obviously, we're going to find different composition in the river water because of that. And you see these evaporites contribute a lot of the sodium that we see in the water and the chloride that we see in the water. And then you'll see this column over here for pollution. Okay. And in some ways, because of the effects of, that I've already mentioned with pollution previously in the class, such as humans evaporate water and concentrate salts, the proportions of salts that we see here are pretty similar to the proportions that we see here. Not exactly, right? There's more sulfur in the pollution than there is these two ions, whereas up here, there's more sodium and chloride. We'll get to sulfur today when we talk about acid rain. That's fossil fuel burning. That's what this one is. That's why it's so much higher. But otherwise, it's kind of hard to distinguish the relative proportion of this, and this in river water without a lot of detailed analysis of the distinction between rainwater in a particular watershed and river water. So there's some fluff. You can move numbers between these columns, but you can kind of see the gist of it here, that human activities have made water saltier in kind of world river water average, especially in those three markets. So there's one other thing we can think about, which is the rocks and watershed, and how do they affect the composition of both the dissolved in suspended load. And the kind of dissolved load is a function of all those features up there. How wet is the environment? How warm or cold is the environment? How much weathering takes place in the environment? And how soluble are all the various chemicals that we're releasing from the rock? So dissolving them is a function of things like temperature and pH and the total organic carbon. So just imagine a watershed like Monongah Valley here, which has got a lot of plant life, very verdant. It's going to be contributing a lot of organic carbon to both dissolved and particulate. We already have talked about the fact that organic matter can really do two important things. It can lower the pH, right? And it can chelate ions. So watersheds that, for if all other things were equal except this proportion, we're going to find more total dissolved solids in this setting. Now, when we come over to suspended load, again, you can see some similarities here, the kind of rock, the climate, we can break down what is in the suspended load into all of the kind of primary inorganic particles we find in the environment, meaning the weathering resistant minerals, ones that just don't break down in soil column and they stay around, things like quartz, titanium oxide is rutile. And then we have low solubility elements and secondary minerals. These are, for instance, clay minerals, so the aluminum and the silicon in there, the potassium to some extent. And then organic particulates, which again kind of goes back to the total organic carbon. And it's just a table showing you for, this is the concentrations of major elements in continental rocks in comparison to rivers, right? So here's the rock concentration, soil, particle, dissolved, particulate load, etc., dissolved load, and then here's the ratio of the two. And the key thing that I want you to notice is that in all of these cases, there's a significant proportion of transported materials in forms that are never dissolved, right? So for some of these elements, the ones in purple, 0.999, 0.998, 0.96, 0.96, essentially all of the transport of aluminum, iron, silicon, and phosphorus are particles. And especially for the case of phosphorus, which is an important nutrient element and kind of limiting for a lot of biological activity in aquatic ecosystems, this insolubility of phosphorus plays a significant role. Now, even for these other elements that I've highlighted in blue, the relative amount of transport in particulates is still pretty high, right? It's 40%, 59%, 36%, so roughly half. And this gives you the idea that a lot of transport of chemicals from the continents through the whole kind of weathering regime into the oceans comes as particulate material. So another thing to think about is the climate for weather. So we know that both temperature, right, how hot, how cold it is, affects solubility, as well as how much water is present, right? If we're in a cold, arid environment, we're not going to get a very different kind of weathering regime than if we're in a hot, wet environment. Another thing that's kind of related to that is the way physical weathering takes place. For instance, roots and burrows and those kinds of things. Think about freeze-thaw cycles in places that do freeze, which help, water gets in, it freezes, it expands, it helps open up cracks. So places that freeze tend to have higher particulate load in, even like once or twice during the year, have higher particulate load, all other things being equal. And so, for instance, if we took a silicate rock, whatever, we could take a rock from the valley here, and we put it in a tropical climate versus a temperate climate, we're going to see different compositions in the water and in the rock. They'll mirror each other, because in a tropical climate, we're going to have more intense weathering. So we're getting a higher proportion of the really weathering resistant elements that I already talked about previously, the silicon, the aluminum, the titanium. And then compared to the temperate climate. The temperate climate, the particulates will hold more of some of the moderately soluble elements. And that's a distinction we'll see, and they'll be less dissolved in the water. So this is an example showing you two things. This first one has runoff. It's a kind of a weird scale. It's like a quasi-log scale. And this is something called the chemical denudation rate. Basically just a measure of how much stuff comes off, measured in tons per square kilometer of watershed area every year. And so you can see that regardless of the type of rock, it's color coded for rock type. The more the runoff, the more stuff comes off, right? Just kind of a one-to-one correlation, although it's a little bit messy. Now we're looking at the rock types, okay? We see that in terrains that have sedimentary rocks, that's this kind of orangish, pinkish color. That's the highest rate of material coming off the continent for a given runoff. Purple is volcanic terrains, and green is plutonic and metamorphic rocks. Think Sierra Nevada, for instance, or the Alps. So you can see that for a given runoff, we get a lot less stuff out of the green zone, the plutonic and metamorphic rocks, than we do from the other. Almost like a factor of 10. That's where the rock type comes from. So you might say, well, why do these kind of rocks weather so much more, both of these and these? And there's a couple of factors. One of them is the internal porosity, how the rocks are constructed, how easy it is for them to break apart and then therefore be transported. Part of it is what chemicals are involved. And in sedimentary rocks, we have some components in some types of sedimentary rocks that are really easy to dissolve and disaggregate. So if we look here again, this is the same data off to the side. Now we're looking at with the rock type, right? So the igneous and metamorphic and the volcanic are still just one bar, but the sediments have been divided up into 3 kinds. Siliciclastic sediments, things like sandstones, carbonate sediments, calcium carbonate rich, and then evaporite sediments. And what you see is that by far, the biggest contribution to this chemical denudation rate is from evaporite material. So if we have them in our watershed, that's going to contribute to much, much higher concentrations. And again, think about human impacts. Any watershed that is now heavily agriculturalized, think about the Mississippi River Basin and all of its tributaries through North America. There's a lot of agriculture distributed through there. Part of what we do is put water on the landscape. That water evaporates, it leaves salt behind. We do that over and over and over again. And that contributes to the saltiness of water coming off that watershed, which makes this bar only higher than it would normally have been without human activity. So over the last 10,000 years, that bar has been growing. This bar is also growing for a completely different reason, which is the supply of acid water to the landscape, again, by human activities, which we'll talk about next, primarily acidification of the atmosphere. These other ones are pretty low, right, or comparably low. So this is sort of, a broad brush of how rock type affects the composition of water coming off the landscape. And here's the very last thing I wanted to show you, which has to do with dissolved silicon. Now, dissolved silica is really, really pH sensitive in its solubility. So not only how soluble it is, but how fast it dissolves. We've talked about before how the presence of organic matter can help to latch on to mineral lattices and help disaggregate them. And that helps with the rate of dissolution. The addition of acid from the organic matter, which lowers the pH and the ability to chelate some ions, all of those things increase the rate at which weathering can take place and therefore transport of dissolved silicon in environments that have a lot of organic. So again, in a wet tropical environment, we're going to find that's warm, we're going to find more dissolved silicon than we are in a cold, wet environment. And then if we shift down to the drier environments, we'll see even less. So this is a plot showing you temperature, mean temperature in a watershed going from -10 up to 30 in degrees C, and the dissolved silicon in milligrams per liter. And you can see the relationship here, positive correlation. It's not super strong, but it's present. And then you can separate out the rock types, right? Volcanic rock versus other kinds of rocks. There's a separation there. So we would, for instance, be a volcanic rock terrain. This distinction has less to do with how soluble the silicon is in the rock as it does with what is the physical form of the rock. How porous is it? How easy is it for it to disaggregate? How much surface area does it present to water as it's weathering? And in volcanic terrains, the materials tend to be more porous and therefore contribute to higher amounts of silicon dissolving in water for a given temperature. And so you can see here, for instance, Iceland, relatively cold setting versus the Philippines. You can see what that difference is. It's like, maybe a factor of 2 or something like that in the total dissolved silica. And we also get like a factor or 2 or so when we look at, in a cold environment, we go from volcanic to not volcanic. Okay, so that was rivers from last time. So now we're going to go on to talk about acid rain today. And we may get through this packet, or it may bleed into next time. We'll just see how we're going. But there's some new reading for this. Okay, so there's some specific pages in Burner and Burner chapter 3. It's up there in that folder with the code BB on it. And there's some reading in a chapter from a book called Turco's the author, chapter 9, called Acid Rain. And the reason, these are coming from different subjects or different books than White is because White doesn't really cover these things. So these are the things that we're going to talk about. We're going to talk about acid sources of the atmosphere and the generation of acid rain. Like, what is that? How do we define it? You can find it in natural cases. We have it right here in Hawaii, right next to Kilauea volcano. There's a lot of sulfur coming in the atmosphere naturally. So we'll talk about the two main sources of sulfur for the, of acids to the atmosphere, which are atmospheric sulfur and atmospheric nitrogen. There's a minor contribution from hydrochloric acid too, but it's much less. And then we'll finish up, either today or next time, looking at the impacts of acid. This is a pretty brief summary. This is a topic that we covered in a lot more detail in the environmental geochem class, but I like to bring it up here because it shows, very dramatically how human activities have impacted a certain part of the hydrologic cycle, which then has attendant impacts all the way throughout on things like rates of weathering and the composition of waters as they come off the continents. So, there's some interesting aspects about pH, which we've kind of already highlighted before, such as pH in the hydrologic cycle is primarily set by carbon dioxide system, like solubility of CO2 and the association of carbonic acid and the bicarbonate carbon anion, plus what happens in the biosphere. When we get up into the atmosphere, the biological component kind of fades away. It's not completely zero, but we don't have very much effect on atmospheric water acidity from biological activity, primarily by CO2. And CO2 kind of sets a typical pH. And this pH is dependent on things like the solubility and the temperature. And are there any particles in the atmosphere that are basic or acidic? So it can vary, but a lot of rain is typically around 5, 5.5, something like that. Now, we looked at the Jerem plot for CO2 before, and we know that the carbonic acid system keeps rain between about 4.3 and 6.5. That is the part of the diagram where HCO3 minus bicarbonate is dominant, right? And it's really hard to make the rain lower than this unless we put a different acid in than carbonic acid. And that's the genesis of what we call acid rain. So pretty much all rain, not 100% of rain on the planet, but the vast majority of it is acidic, okay? Mildly acidic. But what we use the word acid rain to talk about rain that is more acidic than it can be made by CO2, something else added to it, okay? And so we can find this naturally, for instance, here in Hawaii, locally, but the vast majority of acidic rain that we find falling on the planet today is from anthropogenic impact. So this anthropogenic impacts are the addition of what we call mineral acids. So SO2, sulfur dioxide, which oxidizes in the atmosphere to SO3, which then dissolves in the water to make sulfuric acid. I'll go through those chemical reactions in a few slides. NO2, which turns into nitric acid when it dissolves in water. And more rarely, some hydrochloric acid, plastics manufacturer, for instance. So these can contribute sources of acid, which can help lower the pH below what we can get from CO2. We also have particles in the atmosphere that are bases, right? Calcium carbonate, gaseous ammonia, to a lesser extent, particles of silicate minerals. They are basic, but they don't dissolve very quickly, and so they rarely contribute much impact to the to the pH of rain. But you can imagine cases where human activities also enhance these things. Agriculture can kick up dust particles in the atmosphere, which can include this. The vast addition of ammonium fertilizers in some cases can result in degassing of ammonia, although if the pH is kept lower, then most of this comes out as ammonium. So it's a localized effect. So before we get on to the acid rain, there's just one other thing I want you to think about, which is this pre-human activities perturbing of the environment sense. The history of life on this planet is directly tied to that germ plot of CO2 in water, right? That's what sets the typical acidity. That's what sets the acidity in our blood, for instance. That's what sets the pH of the oceans. And so a lot of aquatic organisms especially have evolved to live in a relatively narrow range of CO2 capability or acceptability because they likewise rely on that CO2 system to regulate their internal pH. I mean, you can find microorganisms that live in pretty much any environment, very acidic, very basic. We're not talking about those, we're talking about higher organisms. And most higher organisms do have internal fluid pHs that are kind of close to the CO2 water equilibrium values. Now this is a diagram showing you as pH increases, and it's kind of a funny scale. It's got low pH over here, high pH over here. Usually you see it plotted the different, the opposite, with some kind of common, chemicals that might interest you, like, oh, here's carrots, here's soda, there's vinegar, tomatoes, etc. And then a diagram kind of showing you a bunch of different aquatic organisms or organisms that live in and around water and how they're affected by lowering pH. And I've added this red line to the diagram, which is the lower CO2 endpoint. You can see how it basically chops off the diversity, the numbers of organisms in these ecosystems. And this is, broadly speaking, decreases as pH increases through this range, decreases through this range, or acidity increases to a point which very little, is able to survive at lower pH than that. And so you can see, again, for the definition of acid rain set as sort of, people usually just put it as below 5, even though it's probably more like below 4.8 officially, but you see it in a lot of diagrams, it's just basically 5. And then you can see the range here, safe for fish survival, acid rain. There isn't much overlap between. So when we talk about acid rain itself, we're talking about rain. This is now like the traditional pH scale with low on this side, high on that side. Acid rain pretty much sits in this box, somewhere between the pH of typical household vinegar and about pH 5-ish. You can find rain that's more acidic than this, but it's pretty rare. So this is, I would say, kind of a diffuse boundary on this side. And we've looked at this diagram before, we just haven't really highlighted the acid rain part. That one of the things that happens during terrestrial weathering is that water in a hydrologic cycle, as it flows through it, increases in pH until we get into the ocean. And this is largely this effect of silicate minerals in watersheds plus carbonate minerals, as we just talked about in the preceding lecture, contribute base to solution, right? So ultimately, acidic rain that lands on the land surface is going to mostly be neutralized. There's way more rock substrate in most watersheds than there is rainwater to be neutralized, so that rivers rarely run acidic, super acidic, outside the range of what can happen from the CO2 system. You can find it, but it's pretty unusual. But what's happening is that we're enhancing the rate of weathering. We're taking away, as we'll talk about, a lot of the bioavailable elements, the nutrient elements that are needed for terrestrial ecosystems by consistently putting acidic rain onto the environment. In essence, is leaching a lot of important stuff out of the environment that would leach out anyway, but over a much slower period of time. We're enhancing the rate of weathering chemical denudation rate by 1 or 2 orders of magnitude, just by putting some extra acid on there. So this is a very schematic look of the budget of ions in a typical acid ring, right? It's a generic acid ring. It's not a particular one. So it's got acid sources, hydrochloric acid, nitric acid, and sulfuric acid. We talked about this briefly last time, where we can look at the anions and cations in rainwater, and we can subtract out the stuff we think came from sea salts, then we can subtract out the stuff that we think came from terrestrial particles, and anything that's left over is something that we might attribute to human impact. And in this case here, there's a huge amount of sulfur. And when there's a huge amount of sulfur, if that sulfur came out of the oceans, for instance, magnesium sulfate, it would come with a certain amount of magnesium, right? Which you can see here is very, very small. There's way more sulfur than magnesium. So that's not like sea salt. Those are closer to 1-to-1 in seawater. And it's got a lot of hydrogen ions. And when we take magnesium sulfate or calcium sulfate from terrestrial environments and put it in water, we don't change the pH. So the fact that we have a lot of hydrogen ions and a lot of sulfur tells us that this sulfur came in a form that lowers pH, which is the addition of sulfuric acid. So this is, excuse me, how the breakdown of terrestrial components and various kinds of aerosols, both marine and terrestrial, plus sources of base add together along with these acids to make this kind of composition. And like I say, it's schematic. So there's one other thing I just want you to think about a little bit about the atmosphere, which is that we interact with the atmosphere right down here at the very bottom in what's called the troposphere. The lowest level of the atmosphere is pretty much where all the stuff we think about as weather and climate are set. But everything about what happens down here is dependent on stuff that's happening above. Okay, and so this height of the troposphere to stratosphere boundary, which is called the tropopause, varies around the planet. It's very low over the poles and is higher in lower latitudes. So it's actually 10 to 16 is not a broad enough range. It's more like 10 to 20, 10 to 25, depending. But in any event, a lot of the sort of processes that we're going to talk about today happen down here, but they're dependent on something that happens right above, right? So we have an ozone layer, which I'm sure everyone has heard of before. Its ozone is O3. You can see it's written here pretty, small. But ozone forms in the atmosphere by taking some oxygen molecules, O2, breaking them apart into oxygen atoms, and then those oxygen atoms combine with more ozone or more oxygen, O2 to make O3. It's a complicated chemistry, and again, we go through it in the environmental geochem class. I'm not going to go through it here, but I just want to point out that it absorbs a lot of ultraviolet light. That ultraviolet light, which is more energetic than the visible light and the visible wavelength, being absorbed there is one of the things that has allowed the development of life on Earth, on land, outside of water, back in the Archean. Our oxygen comes from photosynthesis. It was a slow buildup. It took 1 billion years or more to get to a high enough concentration that we could start to make this ozone. And once we made that ozone, then we started to filter the more energetic components of light so that it's more comfortable down here on the planet surface in air outside of water, which also happens to absorb UV. So the fact that human activities are also thinning this layer, primarily through the addition of chlorofluorocarbons, which disrupt that oxygen to ozone balance. It's a very delicate balance. Plus the fact that we put particles in the atmosphere primarily through airplane exhaust as we fly above the tropopause. It gives us little active particle surfaces in the atmosphere where chemistry can take place. That layer thinning allows a higher proportion of energetic light to come down into the lower atmosphere, and that affects acid oxide production. So acid oxide production in the atmosphere, and we'll see it in a second on some chemistry slides, is partly enhanced by the promotion of hydroxyl radical. Hydroxyl radical is something OH, is part of water. So if you take water and you zap it with light that's energetic enough, you can split it into an HO and an H. The HO is very reactive and it can interact with other stuff and help oxidize them and also promote the rate of oxidation of chemicals that are acidic in the atmosphere, contributing to acid. So, there's a lot, it's a very complicated system. I don't want to, imply that this summary is everything that happened, but there's several ways combined together that human activities are confounding the hydrologic cycle, especially by increasing the rate of acidification. So now let's look at the sources of these two main chemicals. So remember I said it's sulfur and it's nitrogen. So the sulfur that contributes to acidity in the atmosphere is fully oxidized, but doesn't necessarily have to come that way when it first goes into the atmosphere. So when we burn fossil fuels, we put sulfur into the atmosphere, especially if we burn fossil fuels that came from terrestrial sources, i.e. coal. No such thing as clean coal. There's coal that has experienced more or less pressure and temperature conditions of metamorphosis when it was transformed from plant matter into coal, which, among other things, contributes to how much sulfur is in it. Right? And we've used up most of the good coal on the planet that was relatively low sulfur. It had a lot of sulfur, but the coal that's being used now, especially in places with a real coal-based economy like China, are even worse in terms of how much sulfur comes into the atmosphere when they're being burned. Then we have biological production of various sulfur-bearing compounds, gaseous sulfur compounds. One of them is this DMS chemical. There are other ones. There's one called MSA. These are gases that are emitted by terrestrial and aquatic organisms that get up into the atmosphere, and then they get oxidized by that hydroxyl radical, which I was mentioning, to make SO2, which is an acid. So you'll see I write out radicals in the common form to have a dot, which means an electron, unpaired electron from the breaking of that bond. We tend not to make these in anywhere except the atmosphere. They're not stable if we made them in water, in liquid water. Then we have volcanic sources, right? And volcanoes can emit sulfur in various forms, oxidized and reduced. And that depends a lot on the magmatic phenomena, which we'll talk about later in the semester, the relative proportions. But the punchline is that regardless of the form, if it's already oxidized, great. If it isn't oxidized, it will get oxidized by interaction with hydroxyl. There are other sources of sulfur to the atmosphere as well, but these are the three main ones. And so this is natural, this is natural, this is anthropogenic. So the sulfur is oxidized, right? And this happens in on aerosol particulates, primarily in the troposphere, but some of that sulfur can be transmitted through the tropopause up to the stratosphere, and it oxidizes up there as well. And in addition to hydroxyl radical, we have other oxidants in the lower atmosphere, again, produced primarily by human activities such as hydrogen peroxide, which breaks apart to make two hydroxyl radicals. Ozone, which is produced as part of what we call photochemical smog, the interactions of chemicals that come out of your automobile exhaust if you don't have a battery-based car and interact with light in the atmosphere, and then the hydroxyl radicals. So this is the primary kind of mechanism of oxidation. And this is the chemistry. So whether we're talking about SO2 interacting with one of those three oxidants, hydroxyl radicals, hydrogen peroxide, or ozone, and depending on whether it's a dry atmosphere or a wet atmosphere, any one of these through a series of steps will make SO3, which dissolves in water to make sulfuric acid, or will go directly to sulfuric acid. And this just shows you the mechanism by which water is split to make hydroxyl. And this is even true if we start with a reduced form of sulfur, such as hydrogen sulfide, or this compound, which is biogenic. It's going to interact with one of these three oxidants to make these oxidized chemicals, which dissolve in water to make sulfuric acid. And that's the source of sulfur. So I point out here on this slide, this is from a different textbook, the kind of importance of hydroxyl radicals in many different aspects of chemistry in the atmosphere, not just the acid-base cycle, but other phenomena such as involving the ozone layer and the production and destruction of chemicals such as chlorofluorocarbons that are play a role in that. Again, this is a topic we spent several weeks on this in the environmental chemistry class, but hydroxyl doesn't just oxidize sulfur to make sulfuric acid. It also oxidizes nitrogen chemicals, as we'll see in a moment, to make nitric acid, and it competes with other processes to make oxidized forms of nitrogen, which affect nutrient delivery to the landscape. So it's involved in a lot of different things. Human activities are increasing the standing crop of hydroxyl radicals, amongst other things in the atmosphere. So this is a diagram kind of showing you a flow chart of how sulfur gets up into the atmosphere and then gets oxidized and comes back to the land surface as oxidized sulfur in terms of sulfuric acid. And this got both natural and anthropogenically impacted phenomena on it here. So we've got emissions that come out of aquatic and terrestrial ecosystems. These are primarily organic forms of sulfur that get oxidized in the atmosphere, they're gaseous, such as DMS, which was on a prior slide, MSA, which I've written out here. You don't have to know these names, just kind of remember that they're organic forms of sulfur that are emitted by plants. They're especially aquatic ones, but terrestrial ones as well. There's even some direct emission of hydrogen sulfide. There's just multiple step oxidation. And then there's the production or deposition of sulfate to the land surface along with acid. Now in a dry atmosphere, think like Southern California where there isn't very much rain, much of the oxidized sulfur comes back to the land surface, not dissolved in water, but it's what we call sulfate aerosols, so dry particulates. But when those dry particulates land on plant surfaces, the next time it rains, they're going to dissolve to make acid. So the net effect on the ecosystem is roughly the same, whether the sulfur is dissolved or falls out of the atmosphere as a particulate. Interestingly enough, sulfate particulates are what we get on foggy days. Right, those are the same particles in the atmosphere. They're primarily SO3 solid, and that's why on wet days we tend not to see nearly as much fog in the atmosphere. These are a couple of flow charts with some numbers on it to give you an idea of the relative sources of things. On this diagram here, I've written out the relative proportions of things. And I want to remind you about the hydrologic cycle, which we've already talked about, which has a net transfer of chemicals, of water specifically, from the oceans into the atmosphere, onto the land surface, and then back out across the land. So this cycle kind of runs like this. Right, there's a lot of net evaporation precipitation over the oceans and a lot over the land, but the difference between them is that there's vapor transport in this direction and river runoff that way. We look at the sulfur cycle, it's exactly the opposite. Right, there's more transfer of sulfur in the opposite direction in the atmosphere, and we can see the relative amount of sulfur coming out of the oceans and back into the oceans, and out of land and back into the land. And when you look at them in detail, the relative percentages, the thing that jumps out right away is fossil fuel burning for SO2. Okay, so all these other sources, yep, there's volcanic sources, they're very localized to around volcanoes that account for about 5% of the present annual budget. Biomass burning, human activities, primarily 2%. The biogenic H2S and DMS from land, right, which is basically these arrows here, small. It's not non-existent, but it's small, 0.2%. And coming back out of the atmosphere over continents, 40% of it that comes out is SO4 2-. Since the primary source was this, and since this is acidic, this comes back with a lot of acid. We also have some dry deposition, as I just mentioned, it's about 6%. If you go over the oceans, you'll see roughly the same kind of thing. There's some sea salt that goes up into the atmosphere. It includes magnesium sulfate. It doesn't contribute to rain acidity, but it does contribute a lot of the sulfur that comes back to the oceans in the form of sulfate. There's also some biological productivity and there's some dry deposition. So you could imagine a world where if you took this thing away, right, the fossil fuel burning, this balance would be the opposite, and it would look kind of like the hydrologic cycle. A little bit more sulfur coming out of the ocean and coming out of land, a little bit more sulfur running across the land's surface back into the ocean. So this is a very direct way that we change things. And this change is really just in the last couple hundred years, right? It's not something that goes back to the earliest days of human activity. I mean, we did start when we discovered fire, whenever that was. We did start doing this a little bit, but it's really only industrial scale mining of fossil fuels and burning, which started, you know, whenever that was, mid 1800s. It's also not, these sources are not distributed equally around the globe. So if you look, this is a plot that starts up near the North Pole, goes all the way down near the South Pole, and it looks at kind of average rate of production of three components: anthropogenic, fossil fuel burning, biogenic, and volcanic. And you can see that, and it's normalized up to 100%. So these are proportions; these are not net amounts. So you can see that to a very large extent, the vast majority of the anthropogenic comes from these kind of temperate region, northern hemisphere. Think, you know, United States, think Europe, think Russia, China. There's a belt around the planet where on those latitudes, there's a ton of sulfur coming to the atmosphere from human activities. Not that you don't find it in other places, because you do. Even in the best places, it's still something like 30%, right? But there's less of it, you know, at these lower latitudes. You could do a similar thing for longitude and see it's also not equally distributed. So this slide just kind of illustrates the importance of sulfur in biological systems and the presence of various forms of sulfur in different oxidation states bound up in organic matter, whether it's living biomass and living tissue, which is emitting gaseous forms of sulfur, or it's decaying organic matter on a forest floor, for instance, or on the seabed. There are various sources of sulfur into the environment that then get up into the atmosphere. The ultimate fate of all that sulfur is to get oxidized and to come out as either acid rain that dissolves water or these dry aerosol particles. And this is really why fossil fuel has so much sulfur in it in the first place. Oops, excuse me. The volcanic sulfur source is also a little bit complicated because it depends on a couple of factors. How active is the volcano? Is it erupting or quiescently degassing? What is the composition of the volcanic gas profile of that volcano? They're not all the same. And as you can imagine, this is a picture of Holy Mau Mau back in April, right after the lava lake that we had for a long period of time. You know, it lasted from 2008 to 2018. So and prior to that, at least for several decades, there hadn't been a lava lake. So it was degassing. We're sitting on a little gas plume. It wasn't going up very high, a few kilometers, bending over in the wind. That leads to really localized deposition, right? Just and the deposition is mostly downwind. And if you know your geography at all, you'll know that the Ka'u Desert is on the rain shadow side of Kilauea as you go down to South Point. It's not a desert just because of acid rain. It's a desert because there's a rain shadow as well. But the typical direction of the trays, the typical kind of low height of the plume contributes to addition of acid to the soil, which makes it even harder to support plant life. So it's partly a desert because of the acid deposition. Now, during periods of time where it's erupting more energetically, the gas plume will go higher. And in cases where the plume can go up above the tropopause into the stratosphere, we can get global distribution of particles. Okay, Kilauea doesn't erupt that way, but other volcanoes obviously do. Think about the Hunga Tonga Hunga Ha'apai eruption of earlier this year. So this is some pictures of Mount Pinatubo, which was one of the largest eruptions in 1991 of the 20th century in the Philippines. The Plinian eruption, and it sends particles, ash particles, along with gases up into the stratosphere, which then distribute globally and have an impact on acid deposition. This is a picture from space of this plume. One of the interesting things, and that's the source of it there, is that you can look in the ice caps in Greenland and in Antarctica, and people drill down and get annualized records of deposition. And we could find big spikes of acid in those ice records corresponding with large eruptions, volcanic eruptions. Some ancient volcanic eruptions that we didn't even know about, we discovered through looking at ice. And it turns out that when an eruption happens close to the equator, you see it in both latitudes. When an eruption happens really far north, like think about Mount St. Helens, or really far south, then you see the deposition only in one hemisphere or another. But so this kind of punctuated deposition during the kind of current geological configuration of the planet contributes a little bit of sulfur to rain globally. You can also think about times in the distant past when we had a lot more volcanism, like when various flood basalt terrains were produced on the planet, and they contribute to a lot more acidification in the atmosphere, and they probably have one of the many reasons that we have a correlation between large-scale volcanism and extinctions on the planet. Okay, and so that is a thing. Nevertheless, all that stuff is small compared to human activities that put sulfur into the atmosphere. And this is a table, kind of an old table, but it gives you just a basic breakdown of how much sulfur comes into the atmosphere. And these are in teragrams of sulfur per year from generating of electricity, from heating, from industry, and from other sources. And you can see that the vast majority of it is electricity generation. That's unfortunately still true today. It's getting way better, especially in the last 5 years. But even here in Hawaii, we burn diesel oil, which is very, very dirty with sulfur. And many states in the country do a lot of electricity generation still with coal. And that puts a lot of sulfur into the atmosphere. The coal itself, or the diesel, has a lot of its sulfur bound up in iron sulfide, which we've talked about before when we're talking about redox. It's something that can be oxidized and contribute to acid runoff from mine tailings. When this gets burned and emitted into the atmosphere, it puts various forms of sulfur that are either fully oxidized or partially oxidized into the atmosphere. If they aren't already fully oxidized, they get oxidized in the atmosphere and then come back to the land surface as acid rain. It's also, of course, the source of most of the carbon that we have been adding to our atmosphere. And so there's a small effect on pH, but a bigger effect on global warming and CO2 in the atmosphere. And this is just kind of a summary of what that chemistry looks like. And if we look at the sulfur dioxide emission to the atmosphere from this source, it's going up. It's been going up even in the last decade significantly. Okay, but interestingly enough, and we'll talk about this coming up in the next few slides, but the relative proportion of sulfur to nitrogen is changing, especially in countries like the United States, Canada, Western Europe. This was identified as a pollutant back in the 60s and 70s. And so some countries have made some efforts to limit the emissions. Not great, right? We're still doing way too much, but it's better than it would have been. But it's coming at the expense of other kinds of burning of fossil fuels that are refined, that don't have as much sulfur in them, specifically gasoline, kerosene, jet fuel, those kind of things. And that produces nitrogen oxide, which we'll talk about next. So overall, we've got increasing emissions of sulfur globally and increasing emissions of nitrogen globally, contributing to increasing acidification of the atmosphere. So these are some contour-ish plots, color-coded for the pH, not pH, the sulfur content of the rain, okay? And this is over continental United States. This color-coded for, think green is low and orange is high. So this is a time series. This is 1997, 2002, 94, 2000, 97, 2002. So it goes like this to this, to that, to that. And I think you can see that, like, for instance, over this time period, you go from having a lot of orange to a lot less orange, right? So there's been improvement. You can also see where most of it's happening. It happens in the industrial corridor, of the kind of mid-Atlantic and northeastern United States. There's a lot, they have to, keep their houses with fuel oil during the summer, they burn coal, there's a lot of industry that, there's reasons why this is this way. And it's gotten better, not so much by using less of those sources, but by smokestack emission controls. Okay, so now nitrogen is a little bit more complicated, right? Most of the nitrogen in the atmosphere is N2, excuse me, and that is really stable. That's why it's the dominant form of gas in our atmosphere. The light in the atmosphere, even the energetic light in the upper atmosphere, doesn't really do very much to change nitrogen from that allotropic form. You can find a little bit of nitrogen oxides being produced in lightning strikes and forest fires and stuff, but mostly the nitrogen we find in our atmosphere that is anything other than N2, which means the various oxides of nitrogen, NO2, N2O5, NO, N2O, those are collectively written as NOx. Just means there's some amount of oxygen on the nitrogen. Those mostly come off the land surface. Like I said, there's like a little bit that's produced naturally in the atmosphere, and there's a little bit of ammonia that comes out of soil. But for the most part, in the atmosphere, before human activities, the vast majority of the nitrogen was N2, and any of this stuff that we found in the atmosphere came off the land surface. Human activities have really changed that in the atmosphere, unlike the case for sulfur, where there are some significant natural sources of other forms to the atmosphere. For nitrogen, just even the presence of a lot of nitrogen oxides can be linked directly to human activity. That's interesting. Okay, so this is the chemistry of nitrogen in the atmosphere. And again, I'm just gonna, highlight that many of them involve oxidations with those same three oxidants that we talked about for sulfur, hydroxyl radical, hydroxide, that can take nitrogen in not fully oxidized forms and convert it into a fully oxidized form, which is NO2. NO2 dissolves in water to make nitric acid. Okay. There's some interactions between nitric acid and sulfuric acid that can also help enhance the rate of sulfuric acid production. There's also the fact that a lot of the nitrogen oxide that we find in our atmosphere comes from human activities, primarily what happens in your internal combustion engine if you drive that kind of vehicle. There's enough heat that's generated in the vehicle that is able to combine molecular nitrogen with molecular oxygen to make these things. There are ways of running a vehicle so that it does less of this. Unfortunately, if you run a vehicle to do less of this, it generates a lot of extra unburned hydrocarbons, which are another kind of pollutant to the atmosphere. So there are a lot of trade-offs in how kind of vehicle engines that do internal combustion are designed. But in essence, you either make a bunch of that or you make a bunch of this called volatile organic carbon compounds. In a dry atmosphere, volatile organic carbon compounds react with partially oxidized nitrogen to produce the same NO2. It also happens to produce ozone, which I haven't put up here, but it's part of the chemical irritants associated with photochemical smog. The net effect of human activity in this sense is to put partially oxidized nitrogen in the atmosphere, which gets fully oxidized by oxidants, and then comes back to land surface as acid. Okay, and by far, anthropogenic sources of various forms of oxygen, of oxidized nitrogen, outweigh the natural ones, right? And it's not just fossil fuel burning. There's other stuff. So internal combustion is a main source, but there's other stuff we do that also enhance nitrogen addition to the atmosphere, especially agriculture. So this is really the genesis of nitrogen oxide acid rain. This is a table from another textbook showing you the much more complicated role that nitrogen plays in atmospheric chemistry than sulfur. So depending on how wet or how dry the atmosphere is, it can contribute to, for instance, acid rain or smog, oxidation of the atmosphere. Nitrogen oxides play a role in global warming, stratospheric ozone depletion, etc. So nitrogen is a much more complicated chemistry, but it does contribute a lot to acid rain. This is a plot. This is going from years from, I know this is kind of not very easy to read, but that's 1977. That's 1995. This is from a relatively old textbook, but showing you the gigantic increase in nitrogen concentration in the air, in the atmosphere over the US over this kind of whatever it is, 20-year period. I have some more recent stuff too, but so unlike SO2 over North America, which has been going down in recent years, as I showed you in those various maps, this is going up. It's still going up today, even if we look at a more recent plot. And so this is a similar set of plots for nitrogen as for sulfur, and again, so a tiny series. And you can see the concentration getting a little bit better in the rain, you know, in the latest version of this diagram compared to that. So the net effect is less rain acidity in the part where most of it falls out. The map looks very similar to the sulfur map, with maybe slightly less happening in the kind of mid-Atlantic and interior portions. But, you know, people like to talk about how, you know, oh, there's all this, you know, vehicle use in Western US and that's a major source. But it isn't, in fact, when you look at the nitrogen in the rain, most of it's happening in that eastern part of the country. Then the third acid that we find in the atmosphere is chlorine, as hydrochloric acid. It comes from a bunch of different sources that can produce, you know, the acid addition to the atmosphere, as well as other sources of chloride that don't affect rain acidity, such as road salting with sodium and potassium chloride. But, you know, waste incineration of chlorine and hydrocarbons, things like, you know, PVC, those produce hydrochloric acid. The manufacture those materials produce hydrochloric acid. Hydrochloric acid, and to a lesser extent, hypochlorous acid, which is produced and used primarily in water treatment, are also sources of HCl to the atmosphere, which basically just associates and contributes to rain acidity. But it's our super localized effect. It's orders of magnitude smaller than sulfur and nitrogen globally. So now these are some diagrams of rain pH. Okay, and these are historical diagrams. This is a contour plot. That's the UK. That's Scandinavia. This is the main continent of Europe. You know, France, Belgium. That's Denmark sticking up. And so this is in the 50s. The rain pH 4.7. Yeah, it can still be explained by CO2, but by the mid 70s, there's a big area of rain pH which is too low to be explained by the CO2 system. It requires a mineral acid. And by the 80s, you can see that you have to kind of read out the contours, but the area that's too low to be explained by CO2, which, you know, is somewhere between anything less than 5 and 4.9, is a big, big area. It's also kind of migrated a little bit over the continent, where the source of a lot of the acid oxide production is, especially Germany and Poland on that particular map. But this is the kind of data that led to the realization in the 70s that maybe human activity is producing acid. And that's when it was sort of first identified and tracked. I've got a series of plots from the North America next, which are similar. So it's basically the same time frame, mid 50s, early 70s, 1980, and this blob of low pH associated with the rain is getting bigger and getting lower in pH. Okay? So, and you can see this area receiving very acidic rain, large area of the eastern seaboard by 1980. So in places like this part of North America and in Western Europe, this was recognized as a significant problem. And so efforts were put in place to try and curtail this, primarily by changing the sources of fossil fuels and processes that have not smokestacks that eliminate some of the particulate load in the atmosphere. Not nearly enough, but some. So one of the transitions that happened over this time period is switching from the burning of coal to the burning of petroleum, you know, refined petroleum, which makes sulfur go down and nitrogen go up. So these are concentrations in a lake in upstate New York. So if you go back to these diagrams we're talking about, this is New York here, somewhere up in this northern area. And looking at the kind of relative amount of acid that's showing up there, and you can see that the anions in the water, you know, nitrogen going up, it's just kind of a messy plot, but increasing the sulfur going down. That kind of mimics the trend in a lot of industrialized countries that, let's check the time, a lot of industrialized countries. And you can kind of see that here, that over this period of time from World War II to close to the end of last century, in North America, nitrogen's going up. Sulfur's a little bit complicated, right? There was like, it went up and then there was a drop during World War II, and then coming off of that, then an increase in the 60s. And then starting around 1970, when this realization about acid rain was happening, in those days, it was mostly thought to be based on sulfur, not nitrogen. We started to change our sulfur use, expensive increased nitrogen, so that yes, the rain acidity in that sense did diminish a little bit, but we just kind of swapped one kind of acid for another. And this is something similar from the UK. This is showing you urban levels of sulfur dioxide in the atmosphere. This is the total energy use. Hasn't really changed over this time period, but what did change is going from dirty sources of gas to natural gas, which doesn't have as much sulfur in it. And it also burns relatively cool, so it doesn't make a bunch of nitrogen. Now, this isn't all kind of doom and gloom. This is a plot showing you over the period 1990 to 2010, a bunch of different chemicals in the atmosphere. But as you can imagine, when we put particulates in the atmosphere that affect the composition of rain and the particulates or dissolved components that come back to land surface, is not just sulfur, it's other stuff too. So for instance, organic aerosols are plotted on here, the sulfate plus nitrate, which is the effect of the dissolution of the rain, inorganic aerosols, particulates that we kick up into the atmosphere, black carbon, think about the soot that you see when you're behind a bus or you're over there, you know, waiting to get your flame before a whopper and you see the stuff coming out of the smokestack. We put a lot of carbon in the atmosphere. Nitrogen dioxide, carbon monoxide, all these things are going down, right? In this particular you know, set of data over the United States, this was published in, you know, in 2017. So it's encouraging for some countries. Unfortunately, the bulk of the world is not putting the same kind of effort into this as is happening in the United States. There's nearly enough in the United States either, in my personal opinion. But you know, these are things that are reversible. There are trends that you know, with kind of effort and money, you can improve these. So this is rain pH over the U.S. Continental U.S. 94, 97, 2000, 2002 again. And you can see orange being the kind of really acidic rain and green being not so acidic. And you can see that, you know, the amount of orange is definitely going down. Now, when you look globally, you don't really see that. This is global production of both SO2 and NO2. So whereas in North America and in Western Europe, you see this thing not increasing over this period and this one increasing as we've switched from coal to refined hydrocarbons. The rest of the world, you just see both of them increasing. And in fact, the vast majority of the increases happened since the year 2000, was primarily from China. So you can see this plot here. This is kind of global emissions of sulfur in gigograms. And, you know, there's the value plus some kind of uncertainty estimate, which is what makes up this kind of band. You can see here's the production in the United States. This is from the year 1900 to the year 2000. There's China. This starts in 1850, which some people think of as the start of the Industrial Revolution from the perspective of affecting the atmosphere. But you can see here that the U.S., yep, it's had its ups and downs, but in the last sort of almost 50 years, it's going down, whereas in China it's going up. And so they're contributing a lot to the acid oxide emissions. They're not the only ones. There are other countries doing it too. But in terms of the two largest economies on the planet, that's what they're doing with acid. Okay, so, and this is basically the various sources that sulfur comes from. smelting and petroleum and coal and everything else. I think I'm going to skip ahead. Oh, well, there's just a couple more slides, but I basically just want to finish up by saying that there are effects on ecosystems. There are effects on the rate of weathering that takes place because of the acid emissions, and there are effects on human structures like buildings. And those are all illustrated in the last few slides here. So for instance, think about acid as sources of cations to soil, right? Those cations from the hydrogen ions can displace other cations like potassium or ammonium, stuff that soil dwelling organisms, especially plants, depend on as part of their nutrient supply. And so this is basically a map showing you areas where soils are sensitive to acid emission. Those are soils with low CEC clays, like ilmenite, not so much montilonite or smectite. And so in this this is from your reading, and this is a pretty old diagram, it's about 25 years old, but it shows you areas where the soils are sensitive, areas where the acid emission is happening. You can see where the overlap zones are, and then current problem areas and potential future problem areas. Like I say, if you were to draw the same map with modern data, pretty much everything that's in the red here is now currently receiving it. And the main gist of it is that when acid impinges on the soil, it displaces other cations, acidifies the soil, and changes its ability to complex ions or to sorb chemicals onto clay surfaces. It also affects things like the solubility of some chemicals like aluminum, which is very toxic to many organisms, especially aquatic organisms. And again, in that natural range of pH set by the CO2 system, aluminum is relatively low. So most organisms don't have to develop strategies to deal with high aluminum concentration. These are just some examples of increasing aluminum concentration on a log scale versus pH in upstate New York and off the coast of Sweden, again, due to acid emissions. These are some of the things, you can read through this on your own, but some of the things that happen in soil that when you add acid to it. The final thing I just wanted to mention is that there's obviously effects as well as on human structures. These are, statues that have been affected by acid oxide deposition and a lot of weathering. I think there's a slide here showing you a forest is significantly impacted by having high addition of acid locally. This is in Ohio from acid rain. And so, these impacts are real, they're significant. This is the very last slide, but if you're interested in it, it kind of summarizes how does acid addition from the atmosphere affect the balance of the major cations that we find in soil and in living within the terrestrial biomass, and how is that impacted by addition of hydrogen. And you can see that the flux of these kinds of calcium and magnesium and potassium out of soil goes way, way up when we start to put a lot of acid on the rings. So that's acid rain. Are there questions about that or about rivers?